Welcome everybody to the today's talk. This is a topic that's kind of near and dear to my heart. First of all, I'm David Blevins, and I work in a company called Tommy Tribe, and we do a lot of stuff around an app server called Apache Tommy. A couple years ago, we had a customer roll that out, and then they were like, "Okay, so now what? How do we secure this thing?" And we're like, "Basic auth?" They're like, "No." So we immediately had to start, doing all this research in this space. And there's a very frustrating thing about security standards is that there's just an unlimited number of them, right? And you start reading these things, and they kind of have this big, huge promise at the beginning, and you get halfway in, what feels like halfway in, and then it's just done. And then there are links to like 4 other specifications that you have to read. You start reading those specifications, and you're just getting pointed all over the place, and pretty soon you feel like you know less and less the more you read these things. And you have this phenomena which always occurs, which is you follow one of these links and you're going, "Okay, this is going to be the one that does it for me. If I can just figure this one out, it's going to lock it all in." And you realize you're reading one of the first specifications you read, and you've just done a big loop. And it's incredibly frustrating. Another frustrating factor is that they tend to rename everything that already existed, and they use very complicated terms for things, and that everything is presented as brand new, when in reality it's probably 90% of the same stuff and 10% new, and it doesn't really help you get familiar with what's there in the space, right? And so being part of the Java ecosystem's standards for a very long time, I've been involved in the JCP for over 10 years and worked on Java EE6, 7, 8, EJB3, so on. I know that there's always some people in the specifications that don't like what's happening. And so one of the things that we did to try and get up to speed as quickly as possible is we read all the security standards, of course, but then we would go look at the names of the people who were on the first version of the specification, then look at whose names are not on the latest version of the specification, contact them, ask them what they think, and then they can't stop ranting about all the things that are wrong with the specification. And it gets you a really good way to kind of balance out the spec lead's perspective, which is always that it solves world hunger if you just use it right and you understood it. And so after having gone through all of this, I really wanted to put together a talk that could try and present this harder knowledge in a really simple way, because I think there's something a little bit more difficult about understanding security standards in our industry, is that the people who feel confident enough to present them are usually explaining things at like bit level encryption and algorithms and things like that, and it doesn't really help people who don't already know the space get familiar with it. So this talk is a very opinionated talk. We are going to kind of destroy a lot of the terms that are used, and it's all from the perspective of you're an enterprise and you're trying to replace a basic auth system with something more modern. So this isn't like the login with Facebook, redirect over to me type of a talk. It's we're an enterprise, we're going to run stuff on-prem. How do we do that? Okay, so first thing we're going to do is we're going to go through OAuth. We're going to run through a basic auth architecture, and we're going to take a look at what OAuth 2 looks like before JSON Web Tokens and after JSON Web Tokens. We're going to look at an alternate perspective on how to secure REST endpoints that's basically been pioneered by people from Amazon, and it's basically what Amazon uses to secure all of the $1 billion+ dollars of revenue they do on AWS. They use a technique called HTTP signatures. So we're going to take a look at what that is, and then if there's time, we're going to see what we can do to actually combine these two things together and make like a beautiful 2-factor system. Okay? So I personally find it really difficult to understand a lot of talks when I'm just seeing flat HTTP messages fly by and I don't have a context in which to put it in. So everything in this talk is going to be measured against our baseline architecture. So we're going to say that we had a monolith and we split it up, and now we have 4 microservices hops that we have to make on the back end to complete a request. We're going to say we have 1,000 people on the other side who are all making 3 transactions per second all day. Now that's obviously kind of a really hyper, they really love our service, so awesome, yay us. But that's our basic model that we're going to measure everything by. So that effectively gives us 15,000 TPS from the front and the back, right? 3,000 TPS on the front, that gets 4 more requests on the back, that's 12,000 TPS, 15,000, okay? So, basic auth, all right? Here's the incredibly secure message format that basic auth is, right? What we do is we have this very unbreakable concept of taking the username and the password, gluing it together with a semicolon or a colon, and then base64 encoding that, which, by the way, base64 encoding is the most unbreakable form of technologies that we ever came up with. So I probably can explain it to you afterwards. I don't want to spend time on it. Yeah, I mean, like, if you can, like, Google will probably decode that for you if you just type it in the search bar. You know, So this is obviously terrible because we're transmitting the identity of the person and their password on every single HTTP request. And so what we have is 3,000 passwords per second being sent on the front end, okay? And they all have to get verified against something like an LDAP server or a database. So now we have 3,000 transactions per second going against an LDAP server or a database. Okay, that's not very performant because now this LDAP is the bottleneck of our architecture. Okay, and then on the back end, most people do not lock down the back end. So who uses, who passes credentials around on the back end and secures your back end? All right, see, it's like 4 hands. So not many, all right? So if you did that, you would end up with 15,000 transactions per second against LDAP. That is really, really hard to scale. So what people do instead often is use IP whitelisting. Well, the problem with IP whitelisting is it's the natural enemy of elasticity. I mean, elasticity is you're booting up machines for a short period of time based upon load, and then they go back down when the load is over, and what happens in that time frame? You're creating a whole bunch of IPs, and if you're using IP whitelisting as a way to say this service can talk to this service, what are you going to do? Have like a team of network administrators just typing in IP addresses all day long? I mean, probably there are services out there that will break CAPTCHAs for you, so probably you could do it, but it's not the best usage of resources, right? So IP whitelisting is still in common use, but any people who are trying to become more elastic, they're not going to be able to use IP whitelisting. So another problem with this type of architecture is you end up with services that look like this. Microservice A says to microservice D, give me all of Joe's salary information, and microservice D says, sure, go ahead and have it. You're behind the proxy or whatever security thing we have on the front, so therefore you're safe. I trust you, right? Anybody here work for Target Corporation? Okay, so they had a breach where they lost lots and lots of credit card numbers, and basically it was determined that it was somebody who was once a contractor and knew all their systems. So we locked down the front door, but we let hundreds of people in our 4 walls per year with laptops, and we educate them, and they're temporary workers, and they're leaving. Aren't they a threat also? So if you have a wide open back end, it's sort of like locking the front door with big bolts and a steel door, and then you're just letting all sorts of people in with limited screening on the back end, and you're rotating technical people out on a regular basis. So there is a lot that can go wrong in the back end. You can't trust it. You should not. All right, so let's walk through how a basic auth system looks when it's under a load of an attack, okay? So let's say the evil country of Latveria wakes up one day and decides to hack us at 4 a.m. in the morning. By the way, is anybody here from Latveria? I'm sorry in advance. You're from Latveria? Okay, you're from the Marvel Universe. Very cool. Someone gets the reference. I like it. Okay, that's where Dr. Doom lives in the Marvel Universe. Okay, so here they look like Snidely Whiplash, just because I think he's like the coolest looking cartoon villain ever. All right, so let's say that the evil country of Latveria wakes up and they're sending now 6,000 transactions per second in invalid username and passwords, while we have our 3,000 transactions per second of good users coming in, okay? So we now have 9,000 transactions per second against the LDAP store, which means that bad traffic is able to affect the user experience of good traffic. So this is not great at all. So, of course, we all know that OAuth 2 is the solution to all of this. And its very first version, it solved password problem instantly, and if you ever failed to roll it out correctly, it's just because you didn't understand the specification. So let's go ahead and talk about OAuth 2 as it existed when it first came out. And so the concept of OAuth 2 is that we don't have passwords, and we have these amazing things called tokens. Sounds awesome already, doesn't it? So with a token, every time a device or user logs in on a device, that device is given a token to be used instead of a password. And the advantage is that there's now effectively a token per device that that user has. And if a user loses that device, you simply poke out that token in the database, and all their other devices still can have access. So if you've ever, say, lost your iPad on a plane, like I've done, I could just go to my accounts that I knew I was accessing with that iPad, and I can say revoke access to this device, and I can still get in with my laptop and my phone, and everything's fine, right? So how is this achieved? Well, there's a revolutionary new concept that OAuth 2 brings into our IT world, which is to take the username and password and put them in a form URL post and send them to a web server and get back a short number, right? So this is probably something none of you have ever done before. Put a little username and password login form and post it to a web server. I know you're going to have to adjust to the new world order. It's going to be a very difficult one. So the funny thing is that that was an intentional thing for backwards compatibility, but they renamed it. It's not logging in. It's called grants. So in OAuth 2, this whole login process is grants, and it's a very fun thing. So you get back an access token and a refresh token. When you want to log in, when you want to send a request as that user, you send the access token in the authorization header of the HTTP message, but now you use the scheme bearer instead of basic. All right? So you go ahead and you keep sending many, many requests with the same access token, and bam, eventually you get a 401. So what happened? Now you have to try and get a new access token because it has expired. So this thing we hadn't been using, which is called the refresh token, we now post that to the same place we posted the username and password. We get a new access token refresh token pair, and then we can go ahead and send the new access token as the user, all right? And the goal of this is that we want to be able to expire these credentials without having to make the user log in again, all right? So this mechanism gives us a way to basically refresh this temporary password that's specific to that device so that if it's ever seen on the wire, it will stop working at some point. So what have we achieved? You've got a lot more passwords, okay? Anytime that you form URL and post something and you get a short string back and sending that string on every request, you're basically adding just more passwords into the system, right? If someone steals that thing, they can be you. I like to refer to, tokens as basically slightly less crappy passwords, but equally crappy HTTP session IDs. I mean, let's put it in context. Who right now, or at any point in the last 20 years, has posted a username and password into a system, gotten back a short ID, which you had to send on every request, and that was what was used to identify the user on the server side? Basically, a JSession ID. Right. I mean, basically the whole entire room. So how is this revolutionary and changing the entire system? The only thing different is that this ID changes on a regular basis and it's stuck to a device. And so the funny thing is that, you know, imagine how if you couldn't rename all this stuff and you had to be honest about what you were doing, imagine the conversation you might have with a vendor over this technology. You would say, so we're trying to remove our basic auth system. We don't want a password. You know, we're trying to figure out how to phase that out and go in a more modern direction. What's your ideas? And the vendor goes, more passwords. You'd kick them straight out the front door. And so that's effectively what we ended up with. And so it's a bit worse than that, because now we're sending 3,000 TPS in tokens towards the front door, and we have to verify them against a store on the server side, which is like our session store, okay? The problem is that if any of you have any auditing concerns, like who has the need, because of legal constraints, that you need to be able to say, who did this transaction last month or last year? A lot of us have to have at least 2 or 4 years worth of data, like say even 10% of it, so we can audit our systems. If you have that requirement, that means you have to keep these tokens in our database, and the worst thing happens is that over time, these things grow, right? And so if we have what was our center point of failure basically turning into a big data problem. So I'll talk about that in a moment, but it doesn't also solve the problem on the back end. On the back end, we have basically something like this. If we were intending to pass the token from microservice to microservice and use that to try and identify the user who's calling us, microservice A would pass this crazy looking string over to microservice D and say, who the heck is this? And they would say, I have no idea. Let's ask the token server, at which point we have now 12,000 transactions per second, in addition going against this token store, and at which point it promptly bursts into flames because it's processing 55% of all of our network traffic, and then it crashes, and now we have 0 transactions per second going through. And like I say, this is the danger of this system, and the problem is that it grows, the token store grows over time because you're having to keep these tokens around for auditing purposes so you can tell who the user was on this HTTP request sometime in the future. So I've experienced this conversation with a lot of customers where they roll this stuff out and they go, it's working awesome, it's working great, and then 3 years in, it's starting to fail a little bit sometimes, we don't know why, and then 5 years in, they're like, it's completely unreliable, we don't know what happened, we haven't changed any code. Well, the size of your token store grew. If you're exchanging these things at a half an hour and you have 1,000 users, you're generating a lot of tokens per day over 5 years, that's a big data problem. And so our center point of failure is guaranteed to grow over time, and it becomes increasingly terrible. Okay, so effectively, this is an old HTTP session concept, right? So we not only got sold that this is the more modern REST way to do it, but it's actually a stateful way to roll out security. And so it's so funny because you know, here's another little thing. If we want to have a more honest description of access token, we could call it an access pointer or an access primary key. That would probably not sell very well, but it is more honest. I like to come up with, this is what I like to describe OAuth 2 as high-frequency password exchange algorithm. It's a slightly more on-the-nose version of the title. And by the way, if you want any of these slides, go to that URL at the bottom is going to have all the resources for the talk on it. So, and that's on every slide. So you can take a picture of any slide and that will get you what you need towards the end of the talk. All right, so JSON Web Tokens solve this problem. So we're going to talk about how they solve this problem. Before we do that, I'm going to propose a computer science question to us, right? Let's say we have a directory, and we want to know when the contents of files in that directory change. Do we A, look at the date stamp of the files and see when they change? Or B, look at the length of the file and see when it changes? Who says A? All right. Who says B? Who says both? Okay. The correct answer, and by the way, I've done both of those. So the rest of you didn't raise your hand, never had this problem, or not quite as honest as those of us who did raise our hand. So hashing is how you solve this problem. Okay. Hashing is a crazy concept where you can have a very short number that statistically represents all the data, gigs and gigs of data. And it's a hard concept to understand, so I have a couple different analogies, but we have a short period of time, so I'm going to go to the best one. This is not the best one, although I love the snowman involved in this one. Okay. So we're going to say we have a keyboard with 256 keys. It could be 128 keys. It could be 64 keys. A hash can be any size, right? The larger the number of keys, the more secure the hash is. But here's how it works. We have a keyboard with 256 keys. Each key represents a bit. And it starts out at 0. When you press the key, it turns to 1. If you press that same key again, it turns back to 0. So every time you touch it, it's being toggled. When the data comes through, we play it like sheet music. We see arpeggios, we see notes, we see chords, we see melody, we play it all. When the music stops, we lift our hands off the keyboard, and whatever combination of ones and zeros are on each of those keys, that is our hash. And if a note was changed, would I play different keys? Yes. Would I then get a different series of ones and zeros at the bottom? Yes. If you added some more music on the end and I continued to play, then I would be changing that hash. That is effectively how hashes work. It's the art of looking at data that it goes through and shuffling around those ones and zeros in a very deterministic way that everyone would get the same set of ones and zeros. If you played the same music, you would get the same keys pressed. If I played the same music, I would get the same keys pressed, and that's how it works. And so sometimes hashes are also called fingerprints, which is not because of this analogy, but it just so happens to work out really, really well. Okay, so you have this ability to run an unlimited number of data and shuffle up bits in a deterministic fashion such that we can tell if the data is different just by looking at the resulting bits and comparing them. And if I took those fingerprints, could I imply the music? Could I go, oh, well, that's this music and I know how to play it? No, you can't. There's no way you could do that. So basically, it's one way. You can't take a hash and then just spit out 10 minutes of music. It's not possible. So it's effectively a one-way representation of the data. And here's an example. If you had this text file that said, Bears beat the Vikings 33-10, you get these hashes. If you change it from 33-10 to 33-30, you'd get these hashes. And there's many different hashing algorithms, right? So the real trick of all this stuff is how to protect the hash, because if two people don't agree on what the hash is, you need a way to split the tie. Now, the Bitcoin version of this is the greatest, the majority wins. Is that a particularly good solution for security systems? No. The only reason they do it is because they don't want a center authority telling the world who's the boss. So they say the majority of the world wins, right? But if we have 3,000 people on the other side, but we have 6,000 hackers, they're easily going to outnumber. And so we don't want them determining who is the owner of this hash. So we have to use basic encryption techniques to now protect this hashed number. So we could use symmetric encryption, And this is an example. So if basically you would encrypt that hash, you would base64 encode it, you'd put it in the message, you'd distribute a symmetric key. Well, the problem with this is that both sides would have equal ability to both encrypt and decrypt the data. There's no clear authority. I'll propose to you an example of we had this, score, right? Let's imagine that the referee calls the score of the game, hashes that score in a file, and distributes the hash evenly to everybody, but then half the stadium says, no, it was actually this, and then the other half says, no, it was actually that. But they all had symmetric keys to prove it. The same symmetric key. Did we get anywhere? No. So we use asymmetric encryption to protect that hash. And what this would effectively mean is that we would give the referee, the referee would have his or her own public-private key pair, and the referee would hash the score, then would encrypt that hash with his or her private key, put it in the back pocket, distribute the public key to the entire stadium, and the entire stadium could verify that that hash is correct by decrypting the encrypted hash with the public key, see that it works, run the same algorithm, hashing algorithm against the message, and bam. But nobody in the stadium would be able to fake an encrypted hash because they would have to have the private key to do that. And so effectively, this allows us to achieve distributed read-only data. We have data, we hash it, we create a hash, we encrypt that with a private key, we put it in the back pocket, we distribute the data and the public key to everybody, and everybody can verify that the data is true, but nobody can modify it because then the hash will come out differently. And then they would have to encrypt that hash with the private key, which they don't have. So basically a digital signature with asymmetric keys achieves effectively distributed read-only data. So here's a trivia question, and this is one to see how well I am doing as a speaker. If we have, say, 1,000 or 1,000,000 documents, how many private keys do we need to sign 1,000,000 documents? Awesome. Exactly, just one. Okay, so now we're going to revisit OAuth 2 in the light of this technique and see how it impacts our architecture. Okay, so here we have this thing we call the JSON Web Token, which is of course pronounced JOT. I mean, you already knew that, right? That's very obvious. That's how you pronounce W, JOT. I guess that's how they pronounce it in Latveria. It's like in Germany, it would be JVIT. Okay, so it is effectively a signed JSON map. So we have information about the user, we put it in the map, and then we go ahead and base64 encode that information, and we sign it, and then we end up with something that looks like this. Okay? We have the information at the top, which is what hashing algorithm we're using and what encryption algorithm we're using, which is to say how we're signing the token. Then we have the information in the middle, which is the information about the user, and the part at the bottom is the resulting digital signature base64 encoded. So here was our access token previously, and here is our beautiful access token now. I just microphone drop. We all thinking, that's amazing. Of course, most of us are thinking, I want the shorter one, because it's the smaller one, it'll be faster on the network. And I wouldn't blame you for thinking it. That's what I would think, and that's why we have to have an architectural view in order to have the full picture, because otherwise we would just go, I want the small one, it's going to be faster. So there's a subtle but high impact change here, and I'm going to skip this part, but basically what we have is when someone logs in, we go to LDAP, we scoop out information about them, we put that in a JSON map, then we sign that with the private key. The private key stays on the server that does the authentication. Nobody else has the private key. We put a pointer in a database, I'll come back to that in a moment, and we send the access token back, which is now this map, and it's effectively a signed cookie. Okay? So now we have this, the client side holding the state and the server side holding a pointer, whereas before we had a flipped relationship. The client side held a pointer and the server side held the state. So the way you get a JSON Web Token is the same way that you get, we're getting tokens before. Our access token now happens to be a JSON Web Token. The OAuth 2 specification does not define what access tokens look like. And by the way, the OAuth 2 specification says that refresh tokens are completely optional, and how they work is up to the implementation. Yay, standards. Side note. Okay, so now instead of passing that short thing, we're passing the bigger thing, okay? And that looks terrible, but what this does to our architecture is this. Now we have, we're going to say that everybody has to log in once a day, okay? And we're going to say that that means that they're going to hit LDAP, of course, one time per day. So LDAP had 3,000 TPS against it, and now it has 1,000 transactions the entire day. We're going to say that we're going to refresh our access tokens every half an hour, and when we refresh the access tokens, that's our time to revoke people's access and say, you've been forcibly logged out on the server side, either because your device has been reported stolen, or we just don't like you anymore, or you didn't pay your bill, or it's Tuesday and our systems decide to misfunction. So when the calls come in with the access token, we're able to verify that they are valid by simply doing a public key check. We check the digital signature on the token using the public key that we have and everybody has, and if the digital signature does not verify, it either means, one, the data's been tampered with, or two, it wasn't signed by our private key, and either way, we don't care. It's not our access token, and we're going to ignore it. The expiration of the token is in the access token. Does anyone remember why that is safe? Could the user tamper with that expiration and make it say infinite? No, because then the music will play differently, you'll get different chords, you'll get a different hash, and then when we go to verify it, we'll see different numbers and we'll go, this has been tampered with. So either way, we can drop this access token at the front door using only a public key check. So this slide will be there for informational purposes. There's just not enough time to cover that topic. So now what we're going to do is we're going to say we're going to check the access token at the front, and we're going to keep passing it to the back end so they can do the same thing. And so our front end, which is our Nginx or our HTTPD or whatever we have, is going to verify that token. It's going to pass it back, and then every microservice is going to pass it with any requests on behalf of that user. So when microservice A says to microservice D, can you give me all of Joe's salary information, microservice D is going to require that microservice A pass a JWT token that has Joe's name in it, and if it can't, it will not give any information out. This sounds like a small thing, but it's huge. So another example of a big hack was Equifax. And they recently, like last year, had a big breach where they lost 160 million social security numbers because they're one of the government ordained places to hold social security numbers securely on behalf of the United States. And they lost 160 million social security numbers because there was a vulnerability in struts. Once the attackers got in the front door, they were able to do a microservice A to D question and get 160 responses back from people who they couldn't prove that they were operating on behalf of, right? If we had an access token that was required by microservice D, so that if you wanted to get Joe's social security number, you had to present a token that Joe has, which you can only get if you logged in as Joe. That would mean it would be impossible to get 160 million records of anything because you'd have to forge 160 million RSA-signed JSON Web Tokens. And if you can forge 160 million RSA signatures, then you can get anything you want because you can break all SSL for the entire world at will. So this is how you prevent yourself from getting massively attacked. If you do have a security vulnerability and someone does get in the front door, you can greatly limit your exposure by simply not dishing out the data unless the microservice that's calling you can prove that the person on the other side is asking for it. So that is probably the biggest, most important takeaway of this talk. If you understand that, everything else is bonus. This is where you get the majority of your security. It beats all the security scanning tools. It beats any login you can do at the front gate. It beats all of it. If you do checks on the back end, it works. Now, we're going to say Latveria wakes up and attacks, and now they're sending another 6,000 TPS of fake access tokens to our front door. And these are, we know we have a JSON Web Token signed system. And so we're able to check all the tokens, all 9,000 that come in per second with a public key, and 6,000 of those are going to be determined to be invalid because they will have crap signatures, and we can drop them on the front door without hitting any databases or any external systems, because a public key is like maybe 1,000 bytes long, and that's all you need. So for less than 1K of memory and no hops across the network, we can deny 6,000 TPS with very little impact on our system. If you can think of a way that's better than this to deny bad traffic with just using 1K of memory and no external hits to even any databases, I say you're cheating and you just shut your computer off, and then we're talking about like a riddle. But we're talking about actual computer science. So there is really no better way to deny that much traffic. So now we have a system where good traffic is not affected by the bad traffic that comes in. Okay? Better yet, on the back end, we're passing this JSON Web Token, and they can be given, each microservice can be given the public key of the gateway in advance, and then they also can verify the validity of any request that comes in and verify the person on their side as well, and they do not have to make a trip over to that little piece which was our bottleneck in the past, because they have the public key, and you don't need to rotate a public-private key pair very aggressively. SSL or TLS is based upon public-private keys, certificates, and they're good for 2 years. So it means you could distribute a public key to all your microservices, install it on the Docker image, and then just use that to verify all the requests the identity of the users that come in without having to make any hops across the network. So now we truly have stateless and secure architecture. If that front gateway just went down, there would be nearly no impact on the back end. That just means no requests would get anywhere because no one's getting any more access tokens. That thing is there really just to take the burden of refreshing and managing the initial login out of the burden of the back end. So now we're only going to check our pointer of databases every time that we refresh a token. For the sake of argument, we've said we're going to check our database of pointers once every refresh, which is once every half an hour. Using the math of our architecture, we went from 55% of all traffic against that center to 0.55% of traffic against that center. Who think that that's a pretty significant improvement? Whose hands don't work? Trick question, because you wouldn't have raised your hand because they don't work. Okay, so that is the awesomeness of JSON Web Tokens. So we're going to quickly zip by this thing because we got 5 minutes left. We can go a little bit over, but that's what we have. So the Amazon approach to this is slightly different, but once again, it is based on digital signatures. So the net thing that you should understand of this talk is that if you understand how a digital signature works, all this stuff is syntactic sugar. That's carrying 90% of the security. Everything else is just sort of configuration and way to pass things around and shore things up, but ultimately the digital signature is the thing providing the security, and your ability to protect the keys that you pass around, that's the most critical part. So there is a security draft where this is detailed, and it's terrible. I really apologize to you in advance if you go read it. It's only 20 pages. And that includes all sorts of examples that you can actually code to, and there are no references really to any other specifications, and you can read it in a day and implement it in 3. So I'm sorry it doesn't live up to the standard of security to try and confuse you deliberately, but yeah, of course that was all sarcasm. I don't know how much of that comes through. I have a super dry sense of humor. Okay. How you sign an HTTP message is basically like this. There's the incoming message, or rather the outgoing message. You as the client, you create a digital signature. So we're going to say we're Amazon, right? And you are the person on the other side of Amazon. So you go to the Amazon AWS website, you get an API key and an API secret. So who uses Amazon, right? So you all have done this. It's just that the library does it for you under the covers. So that little API key and that API secret is getting used in the following way by Amazon. When you make a request to Amazon, let's say that this is our request, you have to take certain parts of the HTTP message, you have to select them, and then you make what's called a signing string from it. This is our sheet music, okay? And then you hash that sheet music using the algorithm that's agreed upon between you and Amazon, which is SHA-256. Then you encrypt that hash with the API key Amazon gave you. You base64 encode that, and you put that in the message. You send that base64 encoded encrypted hash to Amazon, and then when Amazon, along with your key name, when Amazon receives it, they retrace your steps. They go, okay, we got a message that looks like this. We know that they took these headers to make a signing string, so this is the signing string we get, and then they follow your steps because they have your key also. And if these two numbers don't line up, then Amazon knows that either it's not you or someone's tampered with your message. Either way, Amazon doesn't care. They're not going to honor this request. And so this is a very, very, very simple technique. This specification was written by the person who wrote the identity system for Amazon. Then they left. At one point last year, they were the SVP of development for Oracle and made the decision to open source all of Java EE to Jakarta EE, and then they went off to Salesforce. So smart people, okay? So it doesn't solve the back-end problem, and I don't have much time to show this last technique, but I will hint upon it, and if you want information, I can certainly get it to you afterwards. But there is a problem with JWT access tokens. They contain a lot of information about you, and they're on the wire. So what is more dangerous to have stolen? A username and a password, or a username and something with all of the information about you, including your privileges and what you can do in the back-end system? Clearly the second one. There is nothing in an access token that if someone else picked it up and sent it, that would prevent them from being able to impersonate you. It's basically a passport without a picture. Has all of your information, has official seal on it, but your picture's not on it. So if you drop it on the floor, congratulations, your identity is stolen. Now, OAuth 2 says the answer is rotate these out quickly. Make them only last 5 minutes. So if they steal your password or they steal your token, they can only be you for 5 minutes. Okay? So what we do is when they log in, we give them an access token, and we also give them an Amazon-style API key. We put the name of the key in the access token, and we make them send both on every request. We verify the signed message with the API key that we gave them, and then we just use the access token to take the state concerns out of our backend system, and we continue to pass it from microservice to microservice. The front gate will be that made the access token will be the one to verify the Amazon-style signature. The backend continue to use it just like a regular plain old JWT. The impact of this is that that symmetric key is only seen at this point of the login. From there on out, it's not seen. So it's like we're piggybacking on the concept of OAuth 2 as high-frequency password exchange to be high-frequency Amazon API key exchange. And then we're tying that into the JSON Web Token so that that key name is tied with that token, and when that access token refreshes, we also rotate the key, and we've achieved an amazing, great signature technique that is basically the one-stop shop for all REST API security. So I have this resources at the first link, and of course, we ended up writing an API gateway because there's no way you can have all this knowledge and not get ambitious about doing something like that. We launched that off here at Java 1, or geez, Code 1, sad. And we are doing a promotion where we're going to pick 5 people to do a prototype with for 1 month. It's an exclusive Code 1 thing, so if you want to know more about that, go to the second link, and you've got to sign up basically by Saturday. And we're going to do demos with people over the course of November, and if we think that there's a good relationship there, we'll give you 1 month of our time free to teach your team and roll this stuff out, because we're super aggressive and super honest, and that's how we're trying to support open source and all the stuff that we do. So if you like this talk, go ahead and do this, and thank you so much for your time. Hope you enjoyed it.